right, let's go. Number 10. The volcano that was predicted before it was found. On March 8, 1979, a navigation engineer named Linda Morabito was sitting at the Jet Propulsion Laboratory, enhancing an image from Voyager 1 to check the spacecraft's position against background stars. Instead of stars, she found a strange crescent-shaped cloud rising off the edge of Jupiter's moon Io, a plume of material erupting nearly 300 kilometers into space. It was the first active volcano ever observed anywhere beyond Earth. What makes the timing strange is what happened 3 days earlier. On March 2, 1979, the journal Science published a paper by Stan Peel, Patrick Casson, and Ray Reynolds of NASA's Ames Research Center and UC Santa Barbara, arguing that Jupiter's gravity should flex Io hard enough to partially melt its interior, and predicting that Voyager's cameras might catch the evidence within days. For decades, planetary scientists had treated small rocky and icy moons as geologically dead. Standard thermal history models, the same kind that explain why Earth's own moon has been volcanically silent for over 3 billion years, held that a body the size of Io, roughly matching our moon, should have radiated away its primordial heat long ago and frozen solid. Io broke that rule in the most visible way possible. Voyager's cameras caught not one eruption, but several, and follow-up imaging showed a surface so young it had essentially no impact craters, at all the geological equivalent of finding a person with no wrinkles, despite claiming to be 1 billion years old. The explanation, confirmed almost in real time, was tidal heating, as Io is stretched and squeezed by an orbital resonance with Europa and Ganymede, that mechanical flexing generates enough internal friction to keep large portions of its interior molten. That mechanism did not stay confined to Io. The same tidal heating physics Peel's team used to predict volcanism now underlies the leading explanation for the subsurface oceans suspected beneath the icy shells of Europa and Enceladus, moons that missions like NASA's Europa Clipper, launched in 2024, are specifically built to investigate. More than 4 decades later, the exact structure of that molten interior is still argued over. Some models, following Peel's original work, describe a magma ocean directly beneath a thin crust. Others, building on Galileo magnetometer data analyzed by Krishan Khurana at UCLA in 2011, argue for a partially molten layer sitting beneath a much colder, thicker lithosphere, a structure needed to explain the 10-kilometer mountains Voyager also photographed on a world supposedly too hot to hold them up. The total heat Io produces, estimated near 100 trillion watts, still exceeds what current tidal models can fully account for. Io is still erupting right now. As you watch this, it has never stopped, not once, since 1979. If a small, forgotten moon could hide something like that, what else out here has already broken the rules and simply hasn't been caught yet? Number 9. The radiation that nearly blinded the spacecraft. By the time Voyager 1 approached Jupiter in early 1979, scientists already had a warning. Pioneer 10, which flew past the planet in December 1973, had measured an absorbed dose of roughly 200,000 rads from electrons and 56,000 rads from protons in Jupiter's inner magnetosphere. Results published across a series of science papers in 1974 and 1979 by the mission's fields and particles teams. A whole body dose of about 500 rads is fatal to a human being. Based on those pioneer numbers, engineers hardened Voyager's electronics and built radiation models around a severe but survivable environment, Earth's own Van Allen belts. The only radiation belts anyone had studied up close before Jupiter set the working intuition for what extreme meant. Jupiter exceeded even the revised expectations. As Voyager 1 crossed the inner magnetosphere in March 1979, its low-energy charged particle instrument and cosmic ray subsystem, overseen in part by Stamatios Krimigis at Johns Hopkins Applied Physics Laboratory, recorded electron fluxes along Jupiter's magnetic equator, roughly 10,000 times more intense than anything found around Earth. The radiation was severe enough to visibly damage Voyager 1's own hardware. Its photopolarimeter, built to measure light scattered off Jupiter's clouds and rings, suffered degraded performance from the exposure, and was shut down entirely by 1980, years ahead of schedule. Voyager 1's ultraviolet spectrometer suffered similar radiation-induced damage during the Jupiter encounter, and engineers had to recalibrate it afterward, using data from Voyager 2, whose trajectory kept it slightly farther from the belt's most intense core. Even NASA's Europa Clipper mission, launched in 2024, was deliberately designed to avoid Jupiter's inner belts entirely, staying no closer than roughly 9.5 Jupiter radii, well outside the region Voyager and Pioneer both flew directly through. Scientists still don't have a complete explanation for how Jupiter's magnetosphere accelerates electrons to such extreme energies. Later missions, Galileo in the 1990s, and NASA's Juno spacecraft, which has flown directly through parts of the inner belts since 2016, have tied much of the acceleration to the plasma torus fed by Io's own eruptions. But the precise mechanism that pumps electrons up to such lethal intensities, and how it varies with Jupiter's rotation, remains actively studied, with models still failing to reproduce the full intensity measured at the belt's core. That radiation would kill a human being within minutes. It is generated by nothing more than a magnetic field, and the debris of one moon's endless eruptions. It is still there. Number 8. The magnetic field that doesn't point where it should. On January 24, 1986, Voyager 2 became the only spacecraft ever to fly past Uranus, passing within about 81,500 kilometers of its cloud tops. Aboard was a magnetometer team led by Norman Ness of NASA's Goddard Space Flight Center. Before that flyby, it wasn't even certain Uranus had a magnetic field at all. The encounter itself was strange well before anyone got to the tilt. Voyager 2 detected a bow shock, the point where the solar wind first meets a planet's magnetic field, at roughly 23.7 Uranus radii, and a magnetopause boundary at about 18 Uranus radii, with a peak magnetic field strength of 413 nanotesla, recorded just before closest approach. The spacecraft also found the magnetosphere almost entirely devoid of plasma, a so-called vacuum magnetosphere, paired with radiation belts of trapped particles that had no obvious source, given how little plasma was available to feed them. Dynamo theory, the standard explanation for how planets generate magnetic fields, predicts that convection in an electrically conductive fluid layer molten metal at Earth's core, metallic hydrogen inside Jupiter should produce a field roughly aligned with a planet's rotation axis, the way Earth's, Jupiter's and Saturn's all are, give or take a few degrees. Uranus's field obeyed no such alignment. Ness and his team, publishing in Science in 1986, found a magnetic axis tilted 59 degrees from the planet's rotation axis, with the source of the field itself offset from Uranus's physical center by nearly a third of its radius. It wasn't a simple, centered dipole at all. Later analysis showed quadrupole and octupole components roughly as large as the main dipole. Some researchers initially speculated Voyager had simply caught the planet mid-reversal, in the brief window when a magnetic field flips polarity. That explanation weakened 3 years later, when Voyager 2 found Neptune's field tilted by a similar 47 degrees, and offset by more than half a planetary radius. Two planets caught mid-flip strained credulity. A leading alternative, developed by researchers including Sabine Stanley, proposes the field is generated, not in a deep metallic core, but in a relatively thin shell of electrically conductive ice and water closer to the surface, a fundamentally different kind of dynamo than the one running inside Earth or Jupiter. The story recently became stranger still. A 2024 analysis led by Jamie Jasinski at NASA's Jet Propulsion Laboratory, published in Nature Astronomy, found that Voyager 2 likely caught Uranus's magnetosphere in an unusually compressed state, driven by a burst of solar wind that occurs less than 5% of the time. No consensus has emerged on the internal structure that produces Uranus's field. Humanity has visited this planet exactly once. Whatever normal looks like there, we may not have actually seen it yet. Number 7. The storm the size of Earth that simply vanished. On August 25, 1989, Voyager 2 made its closest approach to Neptune, the only spacecraft ever to visit the planet, coming within about 950 kilometers of its cloud tops. Imaging teams, including planetary scientist Heidi Hammel, then at MIT, documented a massive, dark, oval storm in the southern hemisphere roughly the size of Earth, quickly named the Great Dark Spot. Winds around its edges were clocked above 2,100 kilometers per hour, the fastest sustained winds ever measured on any planet in the solar system. Voyager's instruments recorded the storm drifting toward Neptune's equator at roughly 1.2 degrees of latitude per month during the brief encounter, accompanied by a band of bright, high-altitude methane ice clouds, riding along its edge. Active movement, fast enough to be measured within the flyby itself, rather than something that would only show up across years of separate observations. The comparison scientists reached for immediately was Jupiter's Great Red Spot, a storm continuously observed since the 1830s, and suspected to be centuries older still. Storms of that size, spinning in a stable planetary atmosphere, were assumed to be inherently long-lived self-sustaining systems, with enough angular momentum to persist for generations. Neptune's storm didn't behave that way. When the Hubble Space Telescope, in observations led by Hammel and published in Science in 1995, imaged Neptune again in 1994, just 5 years after the flyby, the Great Dark Spot was completely gone. Not weakened, not merged with another feature, gone, replaced by a new dark spot that had formed in the northern hemisphere, a near mirror image of the one that vanished. Neptune's atmosphere, on a world receiving only about 3% of the sunlight Jupiter does, was somehow generating and dissolving Earth-sized storms on a timescale of a few years, all while sustaining the fastest winds in the solar system on almost no direct solar heating at all. More dark spots have appeared and disappeared since, including one tracked by Hammel using Hubble in 2015, and another that researchers later determined had likely dissipated between 2021 and 2022. Patrick Irwin at the University of Oxford, using data from the European Southern Observatory's Very Large Telescope and publishing in Nature Astronomy in 2023, has proposed that the spots form from darkening particles in a haze layer beneath Neptune's visible clouds. But no one has fully explained where the energy driving Neptune's extreme winds comes from, given how little sunlight the planet receives, or why its largest storms rise and collapse so much faster than Jupiter's. Somewhere in Neptune's atmosphere right now, there may be a storm larger than a continent. No one knows how long it has left. Number 6. The boundary that was 40 times denser than it should have been. For most of 2012 and early 2013, nobody could say for certain where Voyager 1 actually was. The spacecraft's plasma instrument, which would have measured solar wind speed and density directly, had failed back in 1980, leaving the Voyager team to infer its location from indirect evidence. Then, on April 9, 2013, Voyager 1's plasma wave instrument, overseen by Donald Gurnett at the University of Iowa, began detecting locally generated electron oscillations at a frequency of about 2.6 kHz. Searching back through the archive, Gurnett's team also found a second, weaker oscillation event from late October through November of 2012, corresponding to an electron density of about 0.06 particles per cubic centimeter, lower than the April reading, but still far closer to the interstellar value than anything measured earlier in the mission. The smooth rise between those two numbers, the team argued, traced out a density ramp consistent with Voyager 1 easing across the boundary sometime in between, rather than crossing it in a single sudden step. Heliospheric models predicted a specific transition at the edge of the Sun's influence. The heliopause plasma density should jump from around 0.0002 particles per cubic centimeter in the outer heliosphere to somewhere near 0.1 particles per cubic centimeter in true interstellar space, marking the boundary where the solar wind finally gives way to the wider galaxy. The oscillation frequency Gurnett's team detected corresponded to an electron density of about 0.08 particles per cubic centimeter, close to the interstellar value, and roughly 40 times higher than typical outer heliosphere densities. Looking back through older data, the team, publishing in Science in September 2013, found a second, fainter version of the same signal from October and November of 2012, implying the density had climbed smoothly in the months between, and that Voyager 1 had likely crossed the heliopause as early as August 25, 2012, months before anyone on Earth realized it had happened. Not every instrument agreed. The magnetometer team, led by Leonard Berlage at NASA Goddard, found that the direction of the magnetic field around the spacecraft hadn't changed at all during this period, a signature you'd expect if Voyager were still inside the heliosphere. Researchers Len Fisk and George Gleckler argued in subsequent papers that the density increase could instead reflect compressed solar wind still trapped inside the heliosphere, not true interstellar plasma. The dispute over what, exactly, Voyager 1 was measuring in those months was never resolved by simple agreement, only by the accumulated weight of more instruments, over more years, mostly settling on one side. For the first time, an instrument built by human hands sat in the space between the stars. What it found there was already 40 times more crowded than anyone's models had allowed. Number 5. The highway with no on-ramp. Even as Gannett's plasma data pointed toward interstellar space, one of the mission's own instruments told a contradictory story, and it belonged to the same spacecraft. Leonard Berlage, at NASA Goddard, analyzing magnetometer data through 2012, and publishing with Norman Ness in the Astrophysical Journal in 2014, found that as Voyager 1 crossed the region where energetic solar particles abruptly vanished, the direction of the local magnetic field barely changed at all. Heliophysical models built up over decades predicted that crossing from the heliosphere into true interstellar space should come with a distinct rotation in magnetic field direction. The sun's spiraling field lines should give way to a differently oriented interstellar field once a spacecraft left the heliosphere behind. A changing field direction was one of the expected fingerprints of the crossing, alongside the density jump and the vanishing solar particles. Kremigis's own particle data, discussed further later in this list, captured the strangeness of the transition directly. Instruments recorded Voyager 1 crossing what looked like the same sharp boundary 5 separate times over the course of about 30 days in mid-2012, as if the spacecraft were skimming back and forth across a wrinkled, moving seam rather than punching cleanly through a fixed wall. Voyager 1's field simply didn't rotate. Ed Stone, the mission's project scientist at Caltech from its beginning until his death in 2024, and his colleagues described the region instead as a magnetic highway, a zone where the sun's field lines appeared to directly connect with the interstellar field outside, letting lower energy solar particles stream out and higher energy galactic cosmic rays stream in, all while the field's own direction stayed locked almost exactly in place. It behaved less like a wall being crossed, and more like a seam where two different magnetic domains had been stitched together, running, unexpectedly, in roughly the same direction. The unchanged field became one of the strongest pieces of evidence used by skeptics of the 2012 crossing, since a true crossing was expected to look far more abrupt. Some researchers argued Voyager was still technically inside a boundary layer even while surrounded by interstellar density plasma. Others argued the alignment was a geometric coincidence between two very different magnetic environments at that one point in the sky. When Voyager 2 crossed a similar boundary in November 2018, carrying a working plasma instrument its twin had lost decades earlier, it measured a genuine directional shift, but even that didn't fully settle what had happened to Voyager 1, arriving from a different angle 6 years before. The first spacecraft to leave the solar system crossed its own boundary along a seam where two entirely different magnetic fields happened to be pointing almost exactly the same way. No one has fully explained why. Number 4. The hum that should not exist. By 2013, Voyager 1 was confirmed to be traveling through interstellar space, and for the next several years its plasma wave instrument mostly recorded silence, punctuated by occasional loud bursts. Plasma oscillations triggered whenever a shockwave from a solar coronal mass ejection finally reached the spacecraft, sometimes over a year after leaving the sun. Between those events, researchers largely expected quiet, with no local disturbance to excite it. The thin interstellar plasma should have produced little to no detectable signal. That was the working assumption when Stella Koch-Ocker, then a doctoral student in astronomy at Cornell University, began re-examining Voyager 1's plasma wave data from 2017 through 2020, looking specifically at the gaps between known solar events. Working with Cornell astronomers James Cordes and Shami Chatterjee, alongside Donald Gannett and William Kurth from the University of Iowa's original instrument team, Ocker found something continuously present in the data instead. A faint, narrow band signal that never fully went away. Published in Nature Astronomy in May 2021, the finding described a persistent, low-level plasma oscillation running in the background of interstellar space the entire time, not the occasional crack of a solar disturbance, but something closer to a constant, faint drone. Cordes, whose broader research focuses on how radio signals scatter and disperse as they travel through ionized gas, compared the known solar bursts to a single clap of thunder in a storm. What Ocker had found underneath it was closer to a continuous, gentle rain that had simply never been noticed, because nobody had examined the quiet stretches closely enough. He noted that being able to track this ambient hum continuously gives researchers something they've never had before, a way to measure the density of the interstellar medium directly, and in something close to real time, rather than only during the rare, violent moments when a solar storm happens to light it up. The implication reframed what empty interstellar space actually meant. If the plasma between stars produces a persistent signal on its own, that suggests a baseline level of turbulence, or low-energy excitation in the local interstellar medium, that existing models hadn't accounted for. Activity, with no obvious solar trigger, humming along, independent of anything happening back at the sun. Researchers still don't have a full explanation for what continuously excites that plasma in a region with no nearby star to stir it. Ocker and her colleagues have proposed it may reflect turbulence inherent to the interstellar medium itself, but confirming that will require years more of data. The spacecraft may not have the power left to keep sending. 14 billion miles from the sun, in a place assumed to be silent, something has been humming the entire time. No one knows what is making the sound. Number 3. The bubble that isn't shaped like we drew it. For nearly 7 decades, ever since physicist Eugene Parker first modeled the solar wind in the 1950s, the shape of the heliosphere, the vast magnetic bubble the sun inflates around the entire solar system, was drawn essentially as a comet, a rounded nose facing the direction the sun moves through the galaxy, and a long tail trailing tens of thousands of astronomical units behind it. Search for an image of the heliosphere today, and that is still overwhelmingly the picture you will find. The confusion deepened years before OFA's model, in 2009, when NASA's Interstellar Boundary Explorer spacecraft, led by David McComas at Princeton University, discovered an unexpected, narrow ribbon of intense particle emission arcing across the sky, in a pattern no existing heliosphere model had predicted. A feature that still has no fully agreed explanation, and that further complicates any attempt to settle on a single, simple shape for the boundary. Standard heliospheric models, refined for decades from Parker's original framework, predicted that this cometary tail should be the dominant feature of the heliosphere's overall structure, stretching far behind the solar system as the sun moves through the interstellar medium. In 2015, using a new computational model combined with in situ measurements from Voyager 1, astrophysicist Merav Ofer at Boston University and her co-author James Drake at the University of Maryland reached a strikingly different conclusion. Publishing in the astrophysical journal Letters, they proposed that the sun's magnetic field doesn't simply get dragged into a passive tail. Its tension actively organizes the solar wind in the heliosheath into 2 turbulent jets streaming downstream from the heliosphere's nose. The result, in their model, isn't a comet, it is closer to a croissant, a short split structure with no long trailing tail. In a 2020 follow-up, published in Nature Astronomy, Ofer's team refined this further into something closer to a deflated rounded shape, splitting the difference between the original croissant and a sphere. The The reaction from the wider heliophysics community was not gentle. OFA has described being challenged at conference after conference, and rival modeling groups, including researchers such as Nikolai Pogorelov and Vladislav Ismadenov, working from different assumptions about the interstellar magnetic field and neutral hydrogen, have continued producing comet-tailed models stretching for thousands of astronomical units, directly contradicting the croissant picture. Voyager 1 and Voyager 2, the only two spacecraft ever to sample the heliosphere's edge directly, crossed it at just two single points in an enormous three-dimensional structure, nowhere near enough data to settle which global shape is correct. As recently as 2023, researchers were still publishing dueling models, and NASA's proposed interstellar probe concept, which would carry modern instruments deliberately toward the heliosphere's boundary, has been floated as one of the only realistic ways to gather the kind of multi-angle data that could resolve the question, though that mission exists only on paper for now. We do not currently know the true shape of the bubble that has sheltered every living thing that has ever existed, for the whole of its 4.6 billion year history. Number 2. The shield around every human who has ever lived. The same boundary crossing that produced the magnetic highway and Gurnet's density jump produced a third signature, tracked independently by the mission's cosmic ray instruments. As Voyager 1 approached the heliopause through 2012, its cosmic ray subsystem and low-energy charged particle instrument, the latter overseen by Stamatios Krimigis at Johns Hopkins Applied Physics Laboratory, publishing in Science in June 2013, recorded galactic cosmic ray intensities rising in a series of sharp steps, first on May 7, 2012, then again on July 28 and August 9, and finally, most dramatically, on August 25, 2012, at a distance of about 121.6 astronomical units from the Sun. At certain energies, background-corrected electron intensities climbed by a factor of up to roughly 100 across the heliosheath, according to analysis led by William Weber at New Mexico State University. The expectation going in was straightforward. The heliosphere is known to act as a partial shield, its outward-flowing solar wind and tangled magnetic field deflecting a portion of the galactic cosmic rays that constantly arrive from exploded stars elsewhere in the galaxy. Every prior measurement, going back to Pioneer, had shown cosmic ray intensity increasing gradually with distance from the Sun. Models built on that data assumed the shielding effect would fade out the way sunlight fades gradually as you walk from a bright room into a dim hallway. What Voyager 1 found at the boundary was not gradual. The transition arrived in sudden jumps rather than a smooth taper, and once the spacecraft was through, Krimigis's team found something stranger still. The cosmic rays in interstellar space weren't arriving evenly from all directions the way theory predicted. Particles above roughly 211 million electron volts showed a persistent, unexplained deficit specifically in the sector of Voyager's rotating detector, pointed at 90 degrees to the local magnetic field, as if something out there were filtering cosmic rays not just by how much shielding they passed through, but by the precise angle they arrived from, relative to a magnetic field whose behavior, like the one described earlier in this countdown, wasn't cooperating with the models either. This matters beyond pure curiosity. The heliosphere's ability to deflect galactic cosmic rays is one of the reasons Earth's surface, and everything living on it, isn't bathed in a significantly higher dose of high-energy radiation capable of damaging DNA. That shielding effect isn't static. It expands and contracts with the 11-year solar cycle, and over far longer timescales it depends on where the solar system happens to be moving through the galaxy's own uneven distribution of gas and magnetic field, a factor Marav-Ofer and others have specifically flagged as relevant to the heliosphere's overall size. Some researchers, examining cosmogenic isotopes such as beryllium-10 preserved in ice cores and seafloor sediment, have proposed that the solar system has passed through denser patches of the interstellar medium in the past, potentially compressing the heliosphere and temporarily thinning its protective effect. The connection between those past episodes and specific events in Earth's biological or climate history remains genuinely contested among researchers, with no settled answer. The same physics extends well beyond our own solar system. Every sun-like star is thought to blow its own version of a heliosphere, an astrosphere, shielding any orbiting planets from that star's local galactic environment in a similar way. Merov-Ofer, whose heliosphere shape modeling appears earlier in this list, has pointed out that understanding the properties of our own heliosphere is a direct prerequisite for judging whether an Earth-like exoplanet elsewhere is actually shielded well enough to support life on its surface. The same open questions raised by Voyager's cosmic ray data at the edge of our own solar system may be quietly limiting how confidently astronomers can call any newly discovered exoplanet habitable at all. Every human being who has ever lived has spent their entire existence on the sheltered side of a boundary in space. No one knows how much that shield has weakened in the past, or when. Number 1. A message with no one left to receive it. In 1977, a NASA-appointed committee chaired by astronomer Carl Sagan of Cornell University, working with Frank Drake as technical director, Anne Druyan as creative director, and designer John Lomberg, among others, assembled a gold-plated copper phonograph record and bolted it to the side of both Voyager spacecraft before launch. The golden record carries 116 images, greetings recorded in 55 languages, natural sounds of Earth including wind, thunder, and whale song, and 27 musical selections spanning Bach to Chuck Berry to Solomon Islands panpipes. Its aluminum cover is etched with a diagram of Earth's location relative to 14 pulsars, along with playback instructions, and a small sample of uranium-238 whose steady radioactive decay would let a future finder calculate roughly how long the record had been traveling. NASA engineers estimated it was built to remain physically intact and playable for at least 1 billion years. The purpose of the record, as Sagan stated plainly at the time, was to function as a message, a bottle cast into a cosmic ocean, meant to communicate something true about human life to any advanced, spacefaring civilization that might someday intercept one of the 2 Voyager spacecraft in the depths of interstellar space. Built into that purpose, however faint the odds, was the premise that a message needs an eventual audience. The premise runs into a problem that has only sharpened with every year since 1977. Voyager 1 is not traveling toward any star in particular. In roughly 40,000 years, it will pass within about 1.6 light-years of a dim red dwarf currently catalogued as Gliese 445. In the constellation Camelopardalis, a close approach, that in galactic terms is still an almost incomprehensibly vast gulf of empty space, with no plausible way for anything to intercept the spacecraft there. Voyager 2 will not drift near any star for a comparably immense span of time. Neither spacecraft is aimed at anything. Both are simply falling, forever, outward, long before that flyby, humanity's side of the conversation, goes silent. As of 2026, Voyager 1's radioisotope thermoelectric generators, which convert the heat of decaying plutonium-238 into electricity, have been losing about 4 watts of power every year since launch, a slow, physically unstoppable decline built into the half-life of the fuel itself. NASA has been shutting down Voyager 1's scientific instruments one at a time to conserve what power remains. The photopolarimeter in 1980. The imaging cameras and ultraviolet spectrometer years later. The cosmic ray subsystem in February 2025. The low-energy charged particle detector in April 2026. As of now, only the plasma wave instrument and the magnetometer are still transmitting data to Earth, and NASA's own projections suggest the last of Voyager 1's science instruments, and eventually its ability to transmit any signal at all, will fall silent sometime around 2030. Perhaps stretching into the early 2030s, if engineers manage to conserve every remaining watt. The end, when it comes, will not be sudden. Engineers expect a gradual withdrawal rather than a single dramatic failure. Non-essential systems, including onboard heaters and gyroscopes, will be switched off one after another to stretch the spacecraft's dwindling power for as long as possible. Even as the growing distance between Voyager 1 and Earth's tracking antennas makes every remaining signal fainter and harder to detect. It has been called, without much exaggeration, the longest continuous conversation ever conducted across cosmic distance. One that has run almost without interruption since 1977, and that is now measured in a shrinking number of years rather than decades. When that happens, the golden record does not stop existing. It does not stop being, technically, a message. It simply stops being one that anyone on Earth can still confirm we sent. The spacecraft will continue outward at roughly 61,000 kilometers per hour, carrying back and whale song and 55 human greetings, through a galaxy that will have no way of knowing it is there, for a span of time that will, eventually, outlast the Sun itself. Current stellar models give the Sun perhaps another 5 billion years before it exhausts its hydrogen and begins to swell into a red giant, engulfing Mercury, Venus, and very possibly Earth. The record, engineered to survive 1 billion years of interstellar radiation and micrometeorite impacts, may well outlast the planet that made it. There is no consensus among researchers in the search for extraterrestrial intelligence about whether sending a message with such astronomically low odds of ever being received serves any purpose beyond what it reveals about the civilization that sent it. Some have argued the record's value was never really about reaching anyone at all. It was, and remains, an artifact of what an intelligent species chooses to say about itself at the exact moment it first becomes capable of asking whether anyone else is listening. Somewhere past the reach of every instrument we have left to listen with, 2 golden records are still falling outward, carrying the sound of human voices toward stars that will not exist yet, by the time either one arrives anywhere at all. We do not know if anyone will ever hear them. We built them anyway. If you want to see more videos like this, click the video on screen now and make sure to subscribe.